Hi everyone. This is the third video for chapter 18, which will talk about the first law of thermodynamics. So let me go ahead and bring up my paper here. The first law of thermodynamics is really just a statement of conservation of energy. And so what we're going to look at in this chapter, the remainder of this chapter pretty much, and other stuff, is a gas. Consider a gas that has atoms or molecules. Those atoms and molecules will move around. They have some internal energy stored kind of in that kinetic energy in the gas. Now, there are different ways you can change that internal energy. One is by adding or subtracting heat, Q. Another way is by doing work, either work done by the gas or on the gas. So we're going to consider the work done by the gas maybe as it expands. It's going to push on the walls of its container, and in doing that, it's applying a force over a distance as those walls expand. And when we talk about gases, we want to talk about other variables, pressure and volume. Pressure is force over area. Volume is area times dx. So this integral of f dx for work just becomes integral of pressure over volume, PdV, from an initial volume to a final volume. And again, this is the work done by the gas as it expands. If it expands, the work is going to be positive. If it compresses, if you do work on the gas, that value of this integral and the work done here is going to be negative. So again, as I said, the gas has an internal energy. We're going to call that E internal. And it can be changed by heat exchange or work. So our statement of the first law of thermodynamics says the change in internal energy of a gas is equal to the heat done plus the work done by the gas. Now, I have a negative sign here, and the reason for that is work is negative because the work done by the gas subtracts from the internal energy. It makes sense. If you're going to do work pushing walls out, that energy has to come from somewhere, and it comes from the gas. As those molecules hit the wall, they apply the force, and they lose speed, they lose kinetic energy. So that's the reason the minus sign is here in this statement of the first law of thermodynamics. So this is really our statement for the first law of thermodynamics. And it works really for any thermodynamic system. And so what you can do are processes that you can make the gas, you can change the properties of the gas, its pressure, its volume, its temperature. And in so doing, you can change its internal energy. Some of the types of thermodynamic processes you come across are adiabatic. By adiabatic, I mean there's no heat exchange. Q is equal to 0. So from our first law, we see that all of the internal energy is due to the work done by the gas. If you have a constant volume, right, your integral up here is 0. Your volume does not change, so there's no work done by the gas. In that case, all of the internal energy change must come from the heat. It's either added or subtracted from the gas. In a cyclical process, if you go all the way back to where you started, right, meaning that you maybe change the gas and then it comes back to its original pressure, volume, and temperature, well, the internal energy change must be 0, right? You start with the same amount of energy in the gas that you end with. So the heat must equal the work. Now you can also have a free expansion, which means you could let a gas out of a container and it doesn't push against anything. In that case, there's no force, there's no work, right? So basically everything equals 0. You're not exchanging heat. You're just letting the gas expand. So everything equals 0 in that case. All right, so the other thing I want to talk about that we'll see later on before I do an example is what's called a PV, or a pressure volume diagram. So it's often convenient when talking about thermodynamic processes with these gases to draw a graph of pressure versus volume, PV diagram. And so if you consider a certain process as the gas changes, right? It could be expanding, whatever the process is. If I am going this way along this curve, right, I am changing from a certain pressure to a certain other pressure, and my volume is also expanding here, the gas is going to do work. And in fact, just by the definition of the integral, the work is equal to the area under this graph. So work is the area under the graph in a PV diagram. Now, one thing you can do is you could take the, you'll see it when you're expanding, work is positive. What if you went the other way along the same curve? It would be the same amount of work, just negative, right? The work would be done on the gas compressing it. Okay, so we've got some definitions. We'll come back later and see some more PV diagrams. But for now, let me do an example here. This is focused well enough to see. So this example problem is going to use the first law for a certain PV diagram. And the question is, first of all, when a gas expands along the path AC, shown below, it does 400 joules of work, right? So the work along this path is 400 joules, and it absorbs either 200 or 400 joules of heat. We don't know yet what that amount is. So our work AC is 400. QAC is either 200 or 400. It's one of those two, but we don't know what it is. So the question A asks, suppose you are told that along the path ABC, the gas absorbs either 200 or 400 joules of heat. Which of these values is correct? So now we're going along this upper path. Now, first thing to realize along the path ABC is that the work done on that path must be greater than the work done on AC, because the area under that graph, ABC, is bigger. Now, if the work is greater, that also means that the heat must be greater. The reason for this is that when you look at the internal energy change of the gas, it's going to be the same along path AC or ABC. The internal energy change is independent of the path. It only depends on the initial and the final points, right? And so it's kind of like voltage in a circuit, right? You have a voltage change is either you get from one point to another, the voltage change is the same. It's kind of like potential energy. Potential energy only depends on the height, for example, for gravity. So the change in internal energy from A to C is equal to the change in internal from AB to C. And that has to equal heat minus W, right? So this difference must be the same. So if the work done is greater, we need to choose the greater amount of work, 400 joules, for the heat done from A to B to C. So now that we know that, we can answer question B. Given the correct answer from part A, how much work is done by the gas along ABC? Well, delta internal energy has to be I've got to use my smaller heat, right? Because I've found that the heat is 400 joules in ABC, it's got to be less in AC, it's got to be 200 joules. And then minus 400 joules for the path AC, because I'm told the work done from A to C directly is 400 joules. So from that, I can find my change in internal energy is negative 200 joules. Now that's along the path AC, but it must be true that the change in internal energy along ABC is the same. As we said, they begin and end at the same point. So it's also negative 200 joules. Now the work done from A to B, the heat we found absorbed by the gas from A to ABC is 400 joules. So again, using the first law of thermodynamics, delta internal equals QABC minus WABC, we can go ahead and solve for the work done along the path ABC, which is 600 joules. And now you could have maybe figured that out, right? I mean, the difference has to be the same. It's got to be 400 joules there. But this is the answer for part B. So the path AC and ABC are connected, and by the fact, again, that the change in internal energy is the same, no matter how you get from A to C. Now, part C is a little bit easier. It just asks, okay, along CD, the internal energy of the gas decreases by 50 joules. How much heat is exchanged by the gas along that path? Now, the point to realize in this case is that the work done along C to D is 0. There is no area under that part of the graph, right? Its volume does not change. So work is 0, which means delta internal energy equals negative 50 joules, just the heat that was actually taken from the gas. So we see that Q is negative 50 joules. So it can be a little bit tricky using the first law, but it's always just using the first law, delta E internal equals Q minus W, and also the fact that the internal energy change does not depend on the path taken. If you go from one point to another, you can go along any path in a PV diagram, and your internal energy change will be the same.